Okay, let's go ahead and get started today. This is going to be a relatively short lecture because I'm going to give you time to work on this new lab. And hopefully you've gotten lab 5 working or mostly working, because this is going to depend on being able to talk to those same modules. So once you have lab 5 set up and working, you're basically going to wire up another unit in the same way, write a sender program, write a receiver program. We're going to get these things to talk to each other over wireless. And this is the kind of thing that you would do for low-level development. Maybe back when we had the systems programming class, the idea of developing low-level driver kind of things came up. So the kind of thing that you're going to do today is you're going to develop something of a low-level driver to get one of the modules to transmit, the other one to receive. So let's take a look at what we're going to do today. So what we're going to do is you're going to be writing programs that get 2 of those wireless modules to send wireless data to each other. And in this case, they're not really going to send it back and forth. It's just basically one of them is going to create a packet and send it. The other one's going to receive that packet and print it, and then that's going to repeat. So before you start on this lab, make sure you complete lab 5. And before you start digging into this, I would run your lab 5 and make sure that you're getting the values you expect from those registers, which means that you have it wired correctly. That will give you at least some sense that you do have it hooked up correctly, everything is working. You can talk to the module and then start working on this, because one of the things you don't want to do is have problems with this lab and have it boil down to, oh, well, I had a wire in the wrong place, or there was a wire that was disconnected and it wasn't talking. So make sure to do that. And if you get partway through this and it's not working, feel free to reload your lab 5 and test it and say, well, what happened? What went wrong? Is lab 5 still working? Okay, so here's what I want you to do today. Is you're going to write a program, a sender program, and a receiver program. The sender program, the Arduino is going to connect to this. So one of your Arduinos is going to connect to this. It's going to load data onto it into a packet, and then it's going to cause that packet to transmit to the receiver. So that's the basic idea. And the main thing to watch out for here is that, again, you're writing 2 different programs, a sender program and a receiver program. If you want to, you can combine them into one program, and you press S to enter sender mode and R to enter receiver mode. That way you could write the same program and run it on both units. But the main thing to note here is that we're only going to be sending data one way right now. In other words, one of the chips is going to be set up to send, the other is going to be set up to receive. So to get you guys started, one of the things, feel free to look at the data sheet for that chip. I'm going to give you some help with that, and I've created a special file that's a set of hints to get you started on that. But if you look at the data sheet that's in here, that's linked to here, that data sheet can actually be really helpful for you understanding how this thing works. And as a quick aside here, let me just pull up that data sheet quickly and take a look at it. So give me just a second here. And let me switch that over so you can see the data sheet for this. Okay, so here's what the data sheet looks like for that part. And specifically, the parts of that are probably, let me size that so you can see a little better here. The parts of that are going to be most useful to you. Well, you could read through the entire thing, but the part we care about is how do we put packets into it? How do we get it to enter send mode? And if you read through this, there's a bunch of stuff about that. But I tried to make this easier for you. But the main thing, the only way that you really interact with this device is through those the SPI commands and the registers. In other words, that's the only communication interface it has other than the CE pin, which matters. But if we scroll down through this and go to the part where the registers are, you've already been interacting with those registers with your previous lab, with lab 5. So scrolling down to that, that's on page, I believe, 54. And let me make that a little bigger so we can see more of that. There's also this state diagram here that can be somewhat useful for you to take a look at. And that state diagram, as it shows up there, let me move this over so you can see a little better. You notice that this has the states when it powers up, power on resets, it goes to this power down mode. From there, you can have this power up signal. And then at startup time 1.5 milliseconds later, it enters standby mode. If you power it back down with this power underscore up equals 0, it goes back to power down mode. So you notice you can go back and forth between it in standby mode and power down mode. And from standby mode, you'll notice that the way you get to either transmit mode or receive mode is, if I zoom in on that so you can see that a little better. Let me move that over some. You'll notice that to get from standby mode to either transmit or receive mode, you have this CE pin. Now that's an actual pin on the chip. That's one of the ones that you should wear. So if you set the CE pin to 1 for more than 10 microseconds, it moves it into this transmitter settling, and then that goes to transmit mode. So it takes 130 microseconds. So from the time you put CE to 1, it takes 140 microseconds to get us to transmit mode. And from that time, if the transmit FIFO is not empty, it'll transmit. As soon as the transmit is finished with one packet, if CE is then at 0, it'll go back down to standby mode and wait for you to set CE back to 1 again, and then it'll enter that and send a new packet. Now, if CE is 1, we stay here in transmit mode, transmitting things. Now, to enter receive mode, it's the same thing. CE goes to 0, or CE goes to 1, it goes to receive mode. It will stay there receiving packets until CE goes back to 0 and it goes there. So that's toggling a pin. But one of the things, what is this power up thing? Well, that's a bit in one of the registers, the configuration register that powers it up. Also, how do we select between transmit mode and receive mode? Well, notice this is prim RX equals 0 or prim RX equal 1. That's another bit in that configuration register. So when we go look at those registers, how do we tell when we're in receive mode or transmit mode? It's a bit in one of the registers that we set. So we have to be able to write to that register and then change the chip enable to a 1 to either enter transmit or enter receive mode. Now notice here, if we go to power down, power up equals 0, it'll go back to power down mode. And when power up goes to 1, it goes back to standby. So we can control those things through those registers. So the key to understanding this and using it is understanding the registers themselves. And actually, you'll notice power up mode says that's in the config register. It tells us that right there. And it says table 16 on page 23 has those startup times. Well, they're also on this state diagram here on page, what page are we on? 21. All right, so let's go ahead and look at the registers. Let's scan ahead here to the registers, since that's how we interact with this thing. One thing to note before we do that, notice the packets here. The packets have up to 32 bytes worth of payload data. So we can load up to 32 bytes of data in one packet. If you have more than that, you have to use more than one packet. All right, so the part that we're concerned with is the registers and the commands. And if you're really interested, you could read through all this other stuff that's in here. But it makes a lot of it sound more complicated than it really is. All right, so here are the commands. So the commands are read register, write register, read payload, read the receive payload, write the transmit payload. And then there's a flush TX, flush RX. There's one to reuse a transmit payload if you want to send it over and over and over again. There's this write acknowledge payload, read the RX payload width, write the transmit payload with no ACK, and then there's this no op command. Well, the ones that we're going to be concerned with today is we need to, on the sender, we need to write the transmit payload. So that happens, and notice it's up to 32 bytes worth of that we can send. And that is this command. So that command, 10100000. We'll talk about that command later on. But notice to read the received payload, 01100001. So really, these top 4 commands right here are the only ones that we're really going to need to mess with in here. We're going to need to deal with the read register, reading a register, writing a register value, and then reading the transmit or the received payload, writing the transmit payload. So we're going to see that in our code description later on. And how do you deal with these? Same way we did with the stuff to read a register, but notice to write a register, we just add this extra bit right there and still put the register address there to write to the register. Now, what do the registers do? How do we set or access those parts? Well, if you scroll down to page, I believe it's 54, 52, 53, 54, right here. Here's the config register. And notice there's that power up bit, which we want it to be powered up. It starts off powered down. So we're going to have to set that to a 1. And then if we're on the transmitter, we're going to want to set this next bit. And notice these are the bit order. So this is the least significant bit. So really, you want to set that prim RX to 0 when you want to be a transmitter, to 1 when you want to be a receiver. So on one end, you're going to put the power this up and have that be a 0 for the transmitter. So that would be a binary value like this, which is a 2. And on the other one, for the receiver, it's going to be a 3. So you're going to put a 2 in this register. And what I would suggest doing is creating a version of your function like read register, but make it a write register function. And then you could say, hey, write register 0, write it a 2 on the transmitter, write it as a 3 on the receiver, and so forth. And then there's some other registers here that we can deal with. The other one that's going to be especially important to us on the receiver is down here. Well, there's a couple other ones. One is setting your address. The receive address and transmit address, they have this 40-bit address, so you probably want to make a function that sets that. So if you're in a dorm with other people doing this lab, you're not all using the same address, you're not getting the same their packets in your system, they're not getting your packets. And notice with a 40-bit address, there are a whole lot of possibilities there. So if you just randomly pick some address value bytes, then you can set that to whatever you want. But you're going to set the receive address here, and you're going to set the transmit address, which is here. And notice by default, those match. E7 here, E7 there. And we'll talk about how to change those, but it's just a register, just like we read them out. You're going to do the same thing, but you're going to write to them. The other part that's going to be useful to us is this FIFO status register, which is hex 17. So that status register, if you look at the least significant bit of that, it's RX empty, is the receive FIFO empty. You're going to use that on the receiver to know when a packet arrives. So in other words, if you read the RX empty, the FIFO status byte, and bit 0, the least significant bit, meaning the one all the way at this end, if that is a 1, that means the FIFO is empty. If that ever goes to a 0, there's a packet in there. You read the packet out and then print it on the screen to show what the contents are. And when you read that packet out, that will automatically clear that or raise that flag saying, hey, that's empty now. So you basically, every time you see that that FIFO is not empty, read a packet. So in other words, that will stay 1 empty. When a packet comes in, it'll go, oop, no longer empty. Then you can read the packet out. It'll go back to being raised high again. All right, so feel free to refer to the data sheet as necessary, especially those register things. Read the descriptions. Notice the way that this is organized, that the leftmost column over here is the register number, the address of the register. This is kind of the name of that register. And then these things underneath that are how the bits are laid out for that register. So in other words, this is the most significant bit is reserved. It's only a 0. And then the next one is this mask RxDR, mask TXDS, max max RT. Do we encode it as, are we encoding the data using a CRC or enabling the CRC? Are we using a 1-byte CRC or 2-byte CRC? And really, for our purposes on these, you can just set those all to 0 if you want to. You could turn on the CRC processing that adds a layer of like a checksum. It adds a check value to make sure that there's nothing wrong with that packet as it's received, so you don't get corrupted data. It makes getting corrupted data much less common. And then we have this power up bit, which we are going to use, and this prim RX bit, which is basically just saying, hey, is this chip acting as a receiver or a transmitter right now? So that's setting the direction. Okay, so again, notice the layout. This is the register's address. This is kind of the name that you can think of it as, and this is how the bits are laid out. And you'll notice that all of the registers have that same kind of structure here. The only exception to those being 8-bit registers are those address registers. The receive address is the only one we need to change on the receive ones. It does have the ability to receive from 2 different sources and then have this kind of sub-address scheme. We can ignore all of those. The only one we really need to worry about is the receive address for pipe 0 and the transmit address, which is at address 10. The rest of the stuff here, other than that register 17, we don't really need to worry too much about. Okay, so let's switch back to the presentation for a second here. All right, so that's the data sheet. Feel free to look back at that as much as you need to. You can go back and look at that, refer to things, read through things. If there are features you want to learn more about, I would by all means encourage you to look at that. But to make this lab easier, oops, we already were there. Let's go back to here. All right, so to make this lab easier, let's take a look at the assignment sheet, and then I've done something else to make it a little easier for you, and that's take a look at what I'm calling the hint sheet, which if you want to try to solve it without looking at the hint sheet, by just looking at the data sheet like you would more in a job environment or work environment, I would suggest trying that. And if you get stuck, then you can look at my hint sheet, or if you just want to start with a hint sheet and kind of, since maybe you haven't done this before, feel free to take a look at that hint sheet and start with that. But let's go and take a look at those documents here, and that'll get us started. So let's start off with a lab sheet. Let me switch over to that. All right, so here's the lab sheet. Basically, it says the wiring is the same as for lab 5. See the lab 5 sheet for details. And then the idea here is this, there are 2 programs. There's a sender program and a receiver program. So let's look at that sender program. The sender program, it's going to accept a key from the serial port. You should know how to do that now. If the character is G, then print a message in the serial terminal that says go, and then it's going to begin transmitting a packet every 2 seconds. So in other words, 1, 2, packet, 1, 2, packet, 1, 2, packet. And I think you should be able to know how to do that. That you're essentially going to have a loop that every 2 seconds calls a thing that sends a packet. Now, what should the packet look like? It'll consist of the characters MSG : followed by an ASCII representation of the packet number. So in other words, the first packet sent would be like MSG 0, next one would be MSG 1, and the next one would be MSG 2. And the reason we're having that change is so on the receiving end, you can see it sent 1, it received 1. It sent 2, it received 2. So the receiver constantly receiving things, you can make sure that it's a new packet. Now in practice with the packets, rather than just having like a little text string like that, I suppose in practice you would actually send useful data. Like for example, if this chip was used in an Xbox 360 controller, as you move the joystick or press the buttons, it would send out little packets that have, this is the state of the buttons, this is the position of the joystick, this is the state of the D-pad, these are the positions of the triggers. So you'd have some kind of encoding for that, all that information. And as changes happen, those get sent out. to the thing. Now, this chip does have a really cool feature that allows it to automatically acknowledge reception of the packets. So in other words, you can have the sender, when it sends, know whether or not its message was received by the other end or not, without having to have any back and forth communication that we would have to do ourselves. So you could say send, and if it says success, then you would know it got received. We're not going to necessarily worry about that right now. And there is a little bit of a complication with that a lot of the modules that you would buy on a place like Amazon are made with knockoff chips. They're not genuine Nordic semiconductor chips. And the Nordic semiconductor documentation actually had a typo in it. And the people who made the knockoff chips implemented it the way that the typo said, not the way that it really worked. And so the auto-acknowledge, everything else is compatible, but the auto-acknowledge feature will work with a genuine Nordic chip and a genuine Nordic chip, or a knockoff one and a knockoff one. But you cannot mix the two because they inverted the polarity on how the acknowledge works. So just keep that in mind if you ever work on a commercial project with these, or some school project where you want to use these. You either have to make sure you have both ends fake or both ends real in order to use the auto acknowledge feature correctly between them. But anyway, you could, if you're not using auto acknowledge, it doesn't matter. They can all talk to each other. All right. Anyway, that's what the sender program does. Notice if the character S is received, then we want to print a message that says stop and stop transmitting messages. So in other words, you get a G, you're going to set a flag. You get an S, you say stop, you clear the flag. If the flag is set, you send a packet, wait a second, send a packet, wait a second, and so forth. On the receiving end, it's going to be very similar, except on the receiving end, when you press G, the message in the terminal is going to say listener go. And when a packet is received, then you just print the contents of the packet. If you press S, then it stops listening. So the idea here is pretty simple. When you write these programs, you're going to load up the receiver, load up the transmitter or the sender. You're going to say G on both of them, and the sender should be able to say message 0, and the receiver will go, oh, here's message 0, message 1, message 1, message 2, message 2, and so forth. Now, a couple hints that I have on here, and then I have a whole hint document that I created as well. There are setup steps that need to be performed to get the wireless module ready on both the sending side and the receiving side. The other hints here, the commands are different for reading registers and writing registers. When we get to the hint sheet, I'll walk you through that a little bit. The commands are different for reading a packet and writing a packet. So look at the data sheet to help figure that out, or look at my hint sheet. Also, I'm going to suggest using functions to abstract the different commands for the module rather than kind of hard coding everything. So just like for the last slide, you made a read register function, make a write register function as well. Make our read packet function, make a write packet function. So in other words, plan out what you need to do with the module and then write the code to accomplish that. Abstract it so in your code it'll look like, oh, read packet into this buffer or whatever, print the contents of that buffer. Write a packet into that buffer, data packet into that, and transmit it. So this says demonstrate your working system for full credit. To demonstrate that, if you just send me what your output is for both your transmitter and your receiver in like text files, that counts. If you want to send me a video of it working, feel free to do that as well. But these modules are actually pretty cool. Let's look at the hint sheet now, where I tried to make this easier for you. And the way I set up the hint sheet was I kind of said, here's some general functions that you're going to need. And I put little comments here. And so what you're going to need to do is write the code that kind of fleshes out what these comments do. So in other words, write 2 to register 0. That puts it into transmit mode. Write a 3 to register 5 to set the RF channel. Write a 0 to register 01 to turn off all the shock burst behavior, which we're not going to be really needing or using in this. Write a 32 to register 11 to set the number of bytes for pipe 0. We're setting it to 32 bytes. That's the maximum size. And then we're going to write this, call this write TX register function. And this, I was setting the addresses with just these strings. Really, it can be any arbitrary string of 5 bytes. I just made a version that sets it by a 5-character long string. So I set both the transmit address and the receive address to some value like that. Now, in your case, to make sure that your code doesn't interfere with your neighbors, just make up a string or use your initials or your last name or whatever. Parts the first 5 characters of your last name or something like that. And that will make sure that your packets aren't being received by somebody else and theirs aren't being received by yours, as long as those two things don't match. And then after that, we set the CE low for 10 microseconds and then set the CE high and delay for 130 microseconds. And this was that thing that was in that state diagram we looked at. And then config RX, which we're going to need on the receiver, is going to be the same. But notice instead of putting a 2 into register 0, we're putting a 3 into register 0. And then the rest of this is pretty much the same. We do have to make sure we have the same RF channel on both of these. And these support like 126 different channels, so that's another way you can distinguish between one system and another system. Now these flush RX and TX, I made the commands for those to show how you do that. I don't think we really need them for this lab, but if you wanted to implement them, there they are. But essentially, you set this chip select low, send command E1 over SPI, and then set chip select back high. Now, where does this E1 come from? Well, that's from the data sheet for the flush TX command. That's the byte value for the flush RX command. And read register, you should have already made this from the last one. Write TX address. And you'll notice here I have this 0x20. In there, and you'll notice I'm writing to address 10. So this bitwise OR is basically just making sure we have the right bit set for writing to a register. So write RX address is at 0A, so we have 20 ORed with 0A. And then down here, write payload, that's command A0, and then you loop to go through each of the 32 bytes here. Read payload, and I would just statically size those arrays. We'll talk about that in a second. Here's the write register function. This looks a lot like the read register function, except we're ORing that 20 onto the register we want and then sending the value using your software SPI function. So basically, I've provided comments for all of the steps you need to take here in order to do that. And here's the setup for the sender. There's my statically sized payload array. And I kind of gave you a lot of the code here that you're going to need, but you're going to need to do this part. If sending is true, then fill in the payload and then delay for 2 seconds. The receiver, same kind of thing. But notice here, how do we know when something has arrived? We read the Fifo status register, which is hex 17, and then we're going to check that bit, the RX empty bit, which was the least significant bit of that. And if it's 0, then we want to read the payload by calling the read payload function and then print out the message that was returned. And the read payload function was one of the ones that you would have done here. So if you kind of follow this as a kind of like a template where you just need to fill in the stuff that's missing, then it should help you out a lot. But if you want to do it without looking at this code, feel free to start with the data sheet and fill things in from there. But I tried to make it easy for you because I don't want you to spend a whole lot of time struggling with this, because we got another lab coming up next week. We lost a little bit of time due to weather. So I want to make sure we get to the stuff that we want to get covered this semester. So go ahead and, if it helps you, follow this. It really, notice this isn't a whole lot of code to write, especially since each line that I have here is essentially, each comment line here is essentially code. One of the things that I would do first is get your read register working, which you should already have working from Lab 5. Get your write register working, and then test those. In other words, make sure that you can write a 2 to register 0. And what I would do is read back the 2, print it on the serial console and say, hey, when I wrote a 2 and I read it back, did I read back the 2 that I wrote to? And if you got that, then notice this is a lot of writing things to registers in different ways. Okay, so that's pretty much it for the hints. So let's switch back to the presentation briefly here. And that's all we're going to do today as far as the presentation is concerned. You should work on your lab and try to get that submitted. If you're having difficulty with that, again, look at the data sheet, look at that hint sheet, make sure your code kind of matches what's going on there, and make sure you understand like that ORing with 0x20. That's because we want to add that extra bit for write. The other part of it is the address that we're actually writing to. So make sure to look at that code, look at my comments in that. Make sure your code matches that, and if you're stuck and something isn't making sense or something's not working, let me know, and I'm happy to help. But that's it for today. Rest of the time, work on your, make sure you get your Lab 5 working first, and then start on Lab 6. And really, if you started with my hint sheet and just started filling in the code as needed in that, and you understand what's going on, you can get this working by the end of the class period today. It's not that much code, and I've already done the kind of organizational structure. Also remember that this is the Arduino is C language based, so when you have your functions, you need to make function prototypes. Also, all the stuff you learned in systems programming applies. So how do you make an array? How do you pass that to a function? Well, as a pointer. How do you index into that pointer once you have it in the function? Square bracket notation. How do you make sure you don't walk off the end of the array? Got to be careful because C does not prevent you from doing that. So all the stuff from systems programming, hopefully you didn't forget it, because now you got to use that and know how it works. Also, one thing I've seen in the Lab 5 questions I've had is people have been having trouble with order of operations with or operator precedence with the bitwise operators. The bitwise operators have a lower precedence than do the comparison double equal, not equal, greater than, and so forth. So make sure if you're using and an or, and then you want to compare that with, for example, 0, double equals 0, make sure you put parentheses around those bitwise operators, because that has made a difference in at least 5 or 6 people's labs not functioning that I've gotten comments on. All right, so work on that. Stay safe, wash your hands, stay out of the cold. It's pretty cold right now. Stay off the roads unless you really have to go somewhere. And other than that, work on the lab and let me know if you have trouble.